Okay, so welcome to hour 8, I believe, of knot theory, topics in knot theory. We're still doing Hovanov homology. We're still following drawbn.net/mo13. And just a minor announcement. So I got an announcement that there will be a power outage in my building at 2 p.m. So I'm expecting they will be a few minutes late and that it will not interfere with class. But there is a chance that I will abruptly disappear at some point. And if that happens, well, you've been warned. Okay? And also, let me remind you that the Jones polynomial very concisely is a circle to the k goes to q plus q inverse to the k, and an overcrossing goes to q plus a zero smoothing. Basically, you've seen this before, and an undercrossing goes to the same thing but with different coefficients. And I think I wanted to mention a very, very similar, like 3-line, 4-line description of the Hovanov complex. But you have to sort of understand what it says, but I wanted to still mention it. So K of L, the Hovanov complex of a link or a knot, is a chain complex of graded, well, I said vector spaces, but if you work over Z, it becomes Z modules. And everything works over Z just as well. And you need the following definition. So the vector space V is the span of V plus and V minus, where the degree of V plus minus is plus or minus 1. And then the Q dimension of V is Q plus Q inverse. You map a circle to the K to V tensor to the K. And here comes the interesting part, or the interesting summary. So if if you have an overcrossing, then the way the Hovanov complex of it is defined as follows. You look at the Hovanov complex of the zero smoothing. You shift it up by 1. This shift up by 1 corresponds to this Q. Shift all the degrees in everything in it. So all the degrees of everything in it, you shift up by 1. And again, that corresponds to this Q. And then you shift, you look at the one smoothing and you shift all the degrees by 2. That corresponds to this Q squared here. And then you flatten the result. Now, what do I mean by flatten the result? I mean the following. So, the Hovanov complex of the zero smoothing will be defined by induction, right? So, we will basically continue defining by induction until we get to a knot with no crossings, in which case the complex is just the vector space to the K with no differential, and everything is placed at height 0. Okay? But then, so suppose you have defined by induction this thing, and you have defined by induction that thing. So each of them is a complex. So each of them is a chain of spaces with maps between them. So this, for example, will be the complex corresponding to the, sorry, I made them too close, the complex corresponding to the zero smoothing, and this will be the complex corresponding to the one smoothing. Now, in between the two complexes, there will be a map. The map will be defined, well, this is the map here, which in fact we are yet to define, but I already mentioned the ingredients that go into it, okay? So there will be a map going this way, And this is the map that corresponds to the transition from a zero smoothing to a one smoothing. And again, I will mention what it is very shortly. And so you get sort of a complex below, a complex above, and a map between them. But that automatically defines a single complex. And that's this operation of flattening here. So the simplex complex, the single complex is defined by summing along the diagonals. So the chain groups will be the direct sums of the chain groups of the two complexes, and with the differentials being the sum of the original differentials and the vertical differential. And this is actually something that we discussed already. This was exactly the construction of a single complex from a double complex, and there were signs involved. And if you open all the definitions, the signs that I mentioned last time are exactly these signs. Okay? So this is for the overcrossing, and for the undercrossing it's exactly the same, except the degree shifts are different, but also the heights are different. So in the positive crossing, you place the first term at height 0 and the second one at height 1. And so when you take the Euler characteristic and you end up looking at alternating sums, this comes with a sign plus, so this is the plus here. And this comes with a sign minus, and this is this minus here. And for the negative crossing, you put this smoothing at height -1, and so it comes with a sign minus, and this one with at height 0, and so it comes with a sign plus. Anyway, once you do this to a real knot, and that's where I started from last time. I mean, that was a bit too abstract and a bit too hard to follow, so maybe it's easier to follow it on an example. So on an example, we've done it, this is what we've done last time. So basically, you end up generating a cube of smoothings. In this cube, instead of looking at every smoothing and replacing it by q plus q inverse to the number of components, you replace every smoothing by v raised to the tensor power, the number of components, and then with some degree shifts according to the power of q that should accompany that smoothing. And we discussed the signs last time, and beyond the signs, what we need is the differentials. And the differentials come as follows. So this is, I'm still just reminding you. So if you re-smooth, so if you replace a 0 smoothing by a 1 smoothing, one of two possibilities may happen. So either two cycles join to one, in which case we need a map from v squared into v. So whenever we have a re-smoothing that replaces two cycles by one, we place there the map m, which goes from v tensor v. And the other possibility is that the re-smoothing takes a single cycle and breaks it into two, and then we need a map from v into v tensor v. And we call these maps m and delta. And we started looking for which conditions do m and delta need to satisfy so that we will get a complex. And it turns out that we're extremely lucky. Once we satisfy the conditions that make it a complex, the result is automatically, and not automatically, it requires a proof, but the result is an invariant. So sort of, it's somehow easier than it should be. Okay, questions or comments?
So I have a question.
Yeah.
So, for every smoothing, there is associated a complex, but okay. So it starts from K of a link diagram is a complex.
Yes.
And then you also said that K of the disjoint union of several circles is a single vector space.
Yes.
So along the way you have turned a complex into a single vector space.
No, the other way around. I've turned a single vector space into a complex. So what I'm saying, so you can regard this, right? The issue, your complaint is that K of a naught must be a complex, and here it's only a vector space. So what I mean is that this is the vector, so you can regard it as a complex by making it the complex 0 goes to v to the power k goes to 0, and 0 all the way to the left and to the right, where this is in height 0. Okay?
Okay.
So now K is always a complex. Maybe I was maybe it was a mistake to show this little slide. Okay, this summarizes everything, but perhaps it's too condensed. So for example,
I find it helpful, especially after you say that it's actually the vector space is actually a complex.
Yeah. Okay. So maybe, maybe the summary is too condensed, but we did go through the example in detail. I actually still owe you a discussion of the signs. So I told you what the signs are, but I didn't quite, explain why it works, okay? And I don't know, I think I prefer to move on and pretend that the signs issue is the signs work, and maybe go back to the signs later, because it's much more exciting to actually see how it happens, okay? What happens next, Okay, so we need two maps. We need a map M from V tensor V into V, and we need a map delta from V into V tensor V, and these maps need to satisfy some conditions. So the first condition we already discussed, and this is that the degree, so we want the differential to be of degree 0, and because there are degree shifts in the vector spaces, we decided that we need the degree of M and the degree of delta to be -1. So they need to subtract 1 from the degree. So whatever the degree of the input is, the degree of the output should be 1 less. Okay. Do people know what are Hopf algebras? I know some people do. Can people tell me if they don't know what Hopf algebras are?
I do not.
Okay.
I've seen the definition once and then promptly forgot.
Okay. The funny thing is that what we need is not a Hopf algebra. But somehow it's kind of nice to know what are Hopf algebras, if only for the context, to understand what this is not. So maybe I'll briefly tell you what is a Hopf algebra. Okay? Even though keep in your mind that it's actually not what we need. Okay? So here is an aside. Aside, Hopf algebras. So what's a Hopf algebra? Maybe I should start with what's an algebra. So an aside to the aside is what is an algebra. So an algebra is a vector space along with an associative multiplication, and if you want it to say a commutative algebra, then you want it to be a commutative multiplication. But what's a multiplication? So an algebra is a space A, so a vector space, and you need a multiplication. A multiplication is a map M, so with a map M, which goes from V tensor V into V, and the fact that I want the multiplication, so you want the multiplication to be distributive, or in other words, linear in the two inputs, right? I mean, you want A plus B times C to be AC plus BC, right? But to be linear in both inputs is encoded in the fact that it's a map from the tensor product into V, right? The fact that I'm using here the tensor product and not just the set theoretic product encodes in it the fact that this is a distributive multiplication. But I still have to explain what does it mean to be associative and what does it mean to be commutative. So what does it mean to be associative? So if you have such a product, if you have such a map M, then there are two ways to go from V tensor V into V. Namely, you could go first to V tensor V by applying M tensor the identity. So you apply M to the two factors, the output comes into this V, and the last factor you copy to the last factor here, so it's M tensor the identity. And then you can apply M from V tensor V into V, and you went all the way from V cubed to V. Alternatively, I could have gone into V tensor V by applying 1 tensor M, so by applying multiplication to the last two factors and the identity to the first, and then again by applying M to get to V. So the associative law is the fact that this diagram is commutative. Okay? If you don't believe me, let's test it. So look at the generic element here. A generic element here will look like A tensor B, will look like A tensor B tensor C. If I apply M tensor 1, then that multiplies A and B and keeps C in place. So you'll get AB tensor C. And now if I apply multiplication, I'll get, well, A and B were already multiplied, and now I multiply the result by C. And if I went the other way, so if I applied M, 1 tensor M, I will get A tensor BC. And then when I apply M, I will get A times BC. And the commutativity of this diagram is the fact that the two results should be equal, and this is the associative law. So this commutative diagram is called the associativity, or maybe the associativity diagram, I don't know. It's a condition on products. Okay? By the way, there is also the commutative diagram. Sorry, the commutative law. So what is the commutative law? So you start from V tensor V, and there are two ways to go into V. One way is to multiply, and the other way is to swap the two tensor factors. So this is the map that I will call sigma, and it is defined by mapping A tensor B to B tensor A. Okay? And then you apply the map M again, and the commutativity of this diagram is clearly the commutative law. So this is the commutative law. Okay. Well, I'm about to tell you what's a Hopf algebra. I started with an algebra. Now I need to tell you what is a Co Algebra. So what is a Co Algebra? So a Co Algebra is sort of the opposite structure to an algebra in a categorical sense. Meaning, everything is the same, but all arrows go the other way. Okay? So first I'll just write it, and then I'll say a word about it. So a coalgebra C is a vector space along with a map which now is called delta. So you know, if I was consistent and I wanted everything to be reversed, I should have reversed the M and denoted it by upside down M or something like that. Okay? But we're not entirely consistent, so instead of M, we call it delta. Totally inconsistent. We switched from Latin letters to Greek, from lowercase to uppercase, I don't know. Okay? And delta, instead of being a map from A tensor A to A, it goes the other way. So it goes from C to C tensor C. Okay? And then instead of having this commutative diagram, you have the opposite commutative diagram. So instead of starting with three V's and ending in one V, you start with one V and end in three. So, except I changed the name to C, so you go from C to C tensor C using delta, or again to C tensor C using delta, and from C tensor C you can get to C tensor C tensor C in two ways. One way is to apply delta to the first tensor factor and the identity to the second, so the first C becomes two C's and the last one remains. And the other way is to apply the delta to the first tensor factor, to the second tensor factor. Okay? So a coalgebra is a map, is a vector space along with a map like this, such that, along with a map delta, such that this diagram is commutative, and the commutativity of this diagram is called the co-associative law. The co-associative law for the co-algebra. So, by the way, I should have said, with algebras you can speak about algebras with unit, and if there is a unit you need to speak about another commutative diagram which the unit satisfies, and likewise here you can add a commutative diagram for the unit. I think I'll skip it because it's actually not necessary for what we will talk about in a minute. Anyway, a coalgebra is called co-commutative. So not every coalgebra is co-commutative, just like not every algebra is commutative. But a coalgebra is called co-commutative if a similar diagram to the one which is just off the screen is satisfied. Namely, if the following diagram is commutative. So if you start from C, you can go with delta to C tensor C, and then you can swap the two tensor factors, and you come again to C tensor C, but you could have come to this C tensor C directly by applying delta. So a co-algebra is co-commutative if this is a commutative diagram. If this diagram commutes. And finally, what is a Hopf algebra? So a Hopf algebra, sorry, not Hopf. So a Hopf algebra, oh, no, sorry. Before that, I wanted to give examples. So I don't really want to give examples because they will come up in a moment, but I wanted to say what is the standard example of a co-algebra. So basically, if, so you know, let me write it as a very, very short claim. So claim, if A is a finite dimensional algebra, then its dual, then C, which is the dual of A, is just the dual as a vector space, is a co-algebra. And if you want, this basically motivates the definition. So it says, suppose you know that something is an algebra, what structure is there on the dual of that something? And the answer is, the dual is a co-algebra. Indeed, you set delta to be the adjoint of M. So remember, M was a map from A tensor A to A. Whenever you have a map between vector spaces, you have an adjoint map going the other way. So you have an adjoint map going from A star to the dual of A tensor A. In the finite dimensional case, the dual of A tensor A is the dual of A tensor the dual of A. So this will become a map from A dual into A dual tensor A dual, and that's the same as saying that you go from C to C tensor C. And you can check that the algebra axioms, when written in terms of M dual, when written in terms of the transpose, become the co-algebra axioms. Okay. Now, you should interrupt me. You should be angry at me. You should be mad, because you should be demanding that there will be nice, interesting examples. Okay. And there will be, but it will give. But please give me time. Okay. I mean, this is an aside. Okay. And there are wonderful examples. There are exciting examples. But since this is an aside, I'd rather not talk about the lovely examples now, but wait with them for later. And in fact, we're not even done with the aside, because I still need to tell you what is a Hopf algebra. So what is a Hopf algebra? So a Hopf algebra is a vector. So you know what? I'm lying to you, because I'm forgetting axioms related to units and not quite inverses, but I'll put it in quotes because it's not precise, but roughly about inverses. So I'm writing sort of the most, I'm writing the big axioms and dropping the small ones. Okay, but there are a few little ones as well. But so in fact, what I'm defining is probably more like a bialgebra, and even a bialgebra without units. Okay, but so what's a Hopf algebra? It's a vector space which is both an algebra and a Co Algebra at the same time. So meaning, so it has M and delta, and it satisfies associativity and co-associativity, satisfying both associativity and co-associativity, but you also want the two to be compatible. So I have to add a condition, and such that the two are compatible. Now, what is the compatibility condition? So the compatibility condition is a bit hard to write, and it's also where we diverge from what we need. What we need is something else. So I'll write it very, very briefly. So you see, if A is an algebra, there is a standard way to turn A tensor A into an algebra. Namely, so in A tensor A, if you want to multiply A tensor B with C tensor D, you declare it to be AC tensor BD. You basically multiply component by component. So if A is an algebra, then A tensor A is also an algebra. Okay? But we have a map for delta from A into A tensor A. Now, right, this is the map that comes from the Co Algebra structure. And the condition is that this map will be a morphism of algebra, and such that delta, which goes from A to n tensor A, is a morphism of algebras. And it's a bit mysterious and worth talking a lot about, but since it's not what we need, I'm going to skip it. Okay. So now let's go back to what we need. I think we probably need 2 pages. Good. So again, what conditions do, so in our case, we have M going from V tensor V, and delta going from, M going from V tensor V into V, and delta going from V tensor V, from V into V tensor V. And the conditions we have so far are that their degrees, so the degree of M is equal to the degree of delta is -1. Okay, we need more conditions. So first of all, the next conditions are the following conditions are a bit obvious. So again, M geometrically, or well, in the world of diagrams, M corresponded to this operation. Okay, to or you know, if I wanted to write it sort of more suggestively, then it will be this operation. So basically, the smoothing in the middle gets switched from a 0 smoothing to a 1 smoothing, and then 2 cycles became 1. And so we get a map from V tensor V into V. That's M. But you see, there was no way to order these two V's. These two V's don't come with a label. I am the first, I am the second. Okay? Because, I mean, just look at the pictures, right? In the realistic examples, so where we've used an M, for example, was going from here to here. How could you tell if the inner one is first or second, or if the outer one is first or second? And if we were going the other way, if this diagram, if actually the knot was the opposite knot, then the diagram was completely reversed, so we will be going from these two cycles into this one cycle here. We'll be just reversing all the arrows. How could you tell whether this knot is, which of the two is to be considered first? Okay? There's no canonical way to decide which one is first and which one is second. But this means that if I want M to make sense, it must be insensitive to that, right? If I want to use M and get a meaningful map from V tensor V into V, then M must be such that if I flip the two inputs, I still get the same output. So the second condition is if I flip the two inputs of M, the output is the same. But this is exactly the commutativity diagram for M. So M is commutative. Okay, third condition. So in a similar way, delta is delta corresponds to resmoothing, like the smoothing here in the middle, into a different one, so that you get a map from V tensor V, from V into V tensor V, but there is no way to order these two V's. So delta should give the same output. So whatever output gives, if you swap the two tensor factors of V tensor V, you should be getting the same thing. So delta must be co-commutative. Okay, then come the more interesting conditions. So now suppose I have a situation where I have three cycles, and there are like two smoothings in between them. I marked them in red, in green. The green has no meaning except for to indicate where the smoothings are. Now I can swap this smoothing into a one smoothing, and then I'd get this picture. Or I could swap this smoothing into the other type, and then I'd get this picture. And here I could swap, and now I could swap this smoothing again, the smoothing on the right, and I get this picture. And I could come to the same picture by resmoothing on the left. So now what I drew right now is a typical face of the Hovanov cube, right? This is all of these are vertices. This is an edge, this is an edge, this is an edge, this is an edge. And our condition was that the faces must be commutative. But, well, so I want this diagram of maps to be commutative. This diagram of maps corresponds to, so this is V tensor, the upper left is V tensor V tensor V. Now I apply M to the first two factors. There is no canonical order between them, but who cares, because M is already commutative. I already demanded that M will be commutative. So this is, so this goes to V, So this goes to V tensor V using M. This goes to, not M, using M. So the last component is untouched, so this is M tensor 1. Or I could go to V tensor V using 1 tensor M. And in both cases, I go down to V using M. And the condition is that this diagram will be commutative, and in too many words, I told you that the next condition here is that M is associative. Okay, the next condition, condition 5, basically reverse all the arrows. Or in other words, look at the face which starts with a single cycle which contains in it two, should I draw it? Maybe I'll draw it. I'll draw it, yeah. So look at the face which starts with a single cycle that has sort of two, that comes near itself in two places, and then smooth it in re-smooth it in two different ways. So one will give us this picture, and the other will give us this picture, and in here you can re-smooth the thing on the left, and here you can re-smooth the thing on the right, and in both cases you'll get 3 cycles, and so we got a diagram. Now the corresponding vector space diagram will be V goes to V tensor V, goes to V tensor V here, goes to V tensor V tensor V, and if you write the maps, this is precisely the co-associativity. So delta should be co-associative, and pretty much every mathematician that sees this, these axioms will jump and say, oh, and surely there must be a compatibility law that makes them a Hopf algebra. And indeed there is a compatibility law, but it's not the compatibility law of a Hopf algebra, but a compatibility law of a so-called Frobenius algebra, and we will have to talk about Frobenius algebras later, but let me just tell you what is the compatibility law that I skipped. Okay? So the compatibility law that I skipped is, well, basically if you start from here and end here. So suppose you have a diagram in which you have 2 smoothings, this one and that one, and you can choose which one to flip first. So if you flip this one first, you get to the left one first, you get to this picture. If you flip the right one first, you get to this picture. Now, if you flip the right one first, you can now flip the left one, and you'll come to this picture. And if you flipped here, here we flip the left one first, so if you flip the right one now, you'll come again to this picture. This map is M tensor 1. This map is delta. This map is delta. And this map is... No, this is not M tensor 1. It's delta tensor 1, I'm sorry. No, what am I doing? Sorry, I've flipped M and delta. Sorry. Okay, this map breaks a cycle. So it's a delta tensor 1. This map merges two cycles, so it's M. This map breaks a cycle, so it's delta. This map is joins two cycles, so it's M, but it leaves the cycle on the left untouched, so it's 1 tensor M. And so the condition remaining, I think it's number 6, is that delta tensor 1 followed by 1 tensor M is equal to M followed by delta, and that's not the Hopf algebra condition. Okay, having said all this, any questions, any comments? I know this is hard to follow. I'm sorry, I don't know what to say. I wish I had more than 3 minutes. But let me tell you, at the end, it's all immensely easy. So basically, I need to write down what's M. So M is a commutative, co-commutative product of degree -1 on a two-dimensional vector space. So basically, all I have to tell you is where does V plus tensor V plus goes, where does V plus tensor V minus goes, and where does V minus tensor V minus go. I don't need to tell you where V minus tensor V plus goes because by the commutative law I already told you. Okay? So where does V plus tensor V plus go? Well, V plus tensor V plus is of degree 2. Subtract 1, you get 1. The output must be of degree 1. In the vector space V plus, there is only one element of degree 1. So this must be a multiple of V1. I'll put star dot here to say it's a multiple. Okay? Likewise, V plus tensor V minus, well, this is of degree 0 because plus 1 plus minus 1 is 0. Subtract 1, you get degree -1. There's only one element in degree -1, so this must be a multiple of V minus. V minus tensor V minus is of degree -2. Subtract 1, you get degree -3. In our vector space, there is nothing of degree -3. So this must go to 0. So we found M except for two undetermined coefficients. Now what about delta? So delta must map V plus into something and V minus into something else. V plus is of degree 1. The output must be of degree 0. In degree 0, there are two elements, V plus tensor V minus and V minus tensor V plus. And the map cannot distinguish them because the map must be co-commutative. So if I flip the two tensor factors, the map must output the same. So it means that these two possibilities must come with the same coefficient, which means that there is only one undetermined coefficient, and it's the pre-coefficient of all that. V minus, it's 2 p.m., I'll continue for another minute. V minus must go to degree, is degree minus 1, it must go to degree negative 2, so this goes to V minus tensor V minus, and there is an undetermined coefficient here. And the thing that you can check is that if you take all undetermined coefficients and put 1, everything works. So basically, Hovanov homology is sort of simpler than it should be. Everything is the simplest you can make it be. So, but we'll have to talk about it next time. Okay? So I'm sorry. Yeah, I'm sorry. Math, there is a lot. You know, I really shouldn't apologize that math is complicated. Math is complicated. That's the way it is. There is a lot of math. Yes.
May I ask a question?
Yeah.
Yeah. So, yeah, back to the degrees of the maps again. Why they are minor? So, in the complex we are moving from. So is it from left to right? Okay.
Yeah.
And the degrees are increasing.
Yeah. But I want the differentials to be of degree 0. Okay? So basically, look, if in the input this is of degree 2, and this is of degree 1, but then I'm going to shift the degrees, so this will become degree 2 plus some shift, 2 plus 7, and this, the shift will be 1 more. Oh, that was the power failure.